Okay, in this video, we're going to be talking about the vertex form of a quadratic function. In the same way that an absolute value function has a vertex form, so does a parabola. Now, this is going to look very similar to that absolute value equation. So, vertex form of a quadratic function looks like this. F of x is equal to a parentheses x minus h squared plus k. Now we're going to go back and again we're going to review all of those transformations because when a parabola is in its vertex form, we can simply look for transformations and that's going to tell us where the vertex is going to be. So in this case, your h, k is going to be your vertex. This minus h is going to move your parabola to the right h if it's a positive. If the h is a negative, it's going to move it left h. If the k is a positive, it's going to move it up k. If it's a negative, it's going to move it down k. So h and k tell us where our vertex is. And as long as we know our transformations, we don't have to get bogged down into the whole minus h and plus k. The axis of symmetry would be x equals, and if you don't remember, this is where we found the axis of symmetry before. If the axis of symmetry was x equals h, then we plugged in the h here to find your vertex. So these values will always be the same. So there's your axis of symmetry. The a value tells you if your parabola opens up or down. And oddly enough, this a value is actually going to be identical to the a value in the previous, the whole ax squared plus bx plus c. That standard form will have the same a value. So it tells you the width and the direction. It tells you how wide or how skinny that parabola is going to be and if it cups up or down. So why should we use the vertex form? Vertex form shows the vertex on a quadratic function in respect to its parent's function. And if you don't remember the parent function, the most basic parabola is y equals x squared. So we're able to take that y equals x squared and we can describe the movement, the transformations, and we know now where the vertex is located. So describe each function just in review. Let's remind you how the values change the parent function. And again, we're transforming y equals x squared into these different ones. If the plus or minus is inside with the x, as it is here, it's going to move it left and right. However, this one is outside. The plus 9, therefore, is going to move it up 9 units. The minus 2 here, since it's not on the inside with x, is going to move it down 2 units. And any of these you don't remember why I'm doing what I'm doing, you can go back and review those transformation videos. A plus 5 on the inside is going to always work backwards. It's going to move it left. A positive 5 would move it left 5, a negative 5 would move it right 5. So this plus 5 would move it left 5. Then you have a negative on the outside. It's not inside with that x, a negative on the outside. Negatives flip. If it's on the outside, that's going to be a vertical flip. It's going to flip it up and down. The minus 4 on the inside would move it right 4. Always opposite. The minus 1 on the outside would move it down 1, exactly as it says it does. Number 5, you have 2 different transformations. Multiplication is going to stretch and compress. Notice this 1/3 is not inside with the x. Okay, 1/3 is being multiplied by x squared. So therefore, since it's not applied directly to the x, it'll be a vertical. Okay, either stretch or compression. If it's a number smaller than 1, it's going to compress it. So this would be a vertical compression times 1/3. And then finally, the plus 2, as it did before, would move it up 2. So you have 2 different transformations there. The plus 4 on the inside here and the negative 2 on the outside, that's actually 3 different transformations. The plus 4 would move it left 4. The 2 would be a vertical stretch. And again, if stretch, if I can spell it correctly, if it's a number smaller than 1, between 0 and 1, then it's going to compress it. If it's a number bigger than 1, it's going to stretch it by that factor. Now, again, if it were on the inside, it would do the opposite, and it would do it horizontally. Now, the negative is another transformation. The negative would flip it vertically. So So that's going to be a vertical flip, which would flip it across the x-axis. Number 7 said Mason graphed the parent function of a quadratic equation. And again, the parent function will be x squared, y equals x squared. Then he reflected the parabola over the x-axis, translated it 7 units up and 3 units to the right. What is the new equation? Okay, so he took his parent function, and let's deal with, let's see, he reflected it over the x-axis first. So let's do that one first. So y equals x squared, to reflect it over the x-axis, that'd be a vertical flip, so that'd be a negative x squared. Okay, then he, let's see, translated it 7 units up. So we know if we tack on, since it's up and down, we're going to tack that plus 7 on the end. Don't do it inside with the x. However, we do have a transformation that happens horizontally, and that would be 3 units to the right. Now, if we're going to do something left and right, we've got to apply it directly to the x. So I'm going to put some parentheses around that x, and to move it 3 units to the right, I'm going to do minus 3 directly to the x. So again, this would flip it, move it right 3, and move it up 7. Okay, now let's look at some graphs of these vertex forms. Now, let me show you how much easier these things are to graph because it's super easy to find your vertex now. Your parent function is y equals x squared. However, this one's been moved. The vertex here is at 0, 0. If you actually take and look at the graph of y equals x squared, again, it looks something like this. The vertex is here at 0, 0. However, this one's been transformed. This one's been moved right 2 and up 3. So your vertex is right 2 and up 3. So automatically you have your vertex by looking at this vertex form. So we go straight to our vertex, then we simply plug in points on each side. Let's plug in 3, 4, and 5 on one side, 1, 0, and negative 1 on the other side. I'll actually plug these in for you. Let's first find f of 3. So inside parentheses, we're putting a 3 in for x, so we've got to do 3 minus 2, and I'm going to go ahead and do that as I plug it in. 3 minus 2 would be 1. So we now have simply 1 squared plus 3, which would be 4. Let's find f of 4. And again, I always like to do the stuff in parentheses first, so 4 minus 2, let's do that as we write it down. That'd be 2 squared, which is 4 plus 3, which is 7. And then to find f of 5, plugging in 5, subtract inside of parentheses. 5 minus 2 would be 3 to the second plus 3. That'd be 9 plus 3, which would be 12. And again, because of our axis of symmetry, we know on the other side, since the steps are the same, we have 4, we have 7, and we have 12. We plot those points, and we're not able to get them all on there, but we get enough to where we can kind of get an idea of what this parabola is going to look like. Now, another option, you could actually square this out, combine like terms, and you could graph it the old way. But again, I think it's much easier to graph from this vertex form. Now, this one doesn't look like it's in vertex form. However, it is. The reason being is because inside that parentheses with the x, there's nothing. So if you want to think of it like this, it gets moved left or right 0, and then this minus 4 would move it down 4. Your vertex is 0, negative 4. Okay, so that's where we're going to start. 0, negative 4 is your vertex. Your axis of symmetry would be x equals 0 if you need it. It's always going to be the same as this 0 value in your vertex. Your axis of symmetry will always pass through that vertex. Then we're plugging in numbers on each side, 1, 2, and 3, negative 1, negative 2, and negative 3. These should be pretty easy to plug in because we have to square the x, and then we just subtract 4. So we're going to do 1 squared is 1, minus 4 is negative 3. Should be the same value there. 2 squared is 4, minus 4 is 0. Same value there. 3 squared is 9, minus 4 would be 5. Same value there. Plotting those points, here's what our parabola looks like. And then let's just go ahead and connect our dots. And we have the following parabola. Again, reminder as I'm writing this down, the number in front of your x squared, if you have parentheses, the number in front of your x squared, the 1 tells you if your parabola cups up or if it cups down. Since it's positive, it's going to cup up. Okay, the next one, my parabola has 3 different transformations here. It's been moved left 5 and down 1, so that's going to tell me my left 5 down 1 is my vertex. And it's also been flipped. Because that negative out front, this should be an upside down parabola. So let's take and let's plug in some more values. Let's plug, I don't know why there's a big space in between that. So let's plug in maybe -4, -3, and -2 on one side, and then -6, -7, and -8 on the other side. Your vertex is located at 1, 2, 3, 4, 5, -1 right there. Your axis of symmetry, you don't have to draw it, but you do have an imaginary axis of symmetry right here that's cutting it perfectly into two equal pieces. I'll go ahead and plug these in for you. -4, just to show you the steps. F of -4. Bring down the negative. Again, go ahead and work the parentheses first if you'd like as you're writing it down. -4 plus 5 would be 1. Make sure that you always square first, negative second. So 1 squared to be 1, leave the negative in front of it. So -1 minus 1 would be a -2. So when I plug in -4, it gives me -2. If you were to plug in -6, it should give you the same thing, and here's why. When you do -6 plus 5, that would give you a -1. And when you square a -1, you'd get the exact same 1. Okay, so that's the reason it works out to be the exact same value there. F of -3, leave the negative. Inside of parentheses, you have -3 plus 5, which would be 2. Square first, that would be a -4 minus 1, which is a -5. And you can look for patterns here now if you'd like to. We went down 1, then we went down 3. The correct answer here should be down 5, should be -10. Let's test and see. Let's do F of -2. Leave the negative. -2 plus 5 in parentheses is 3. This will be a -3 squared is 9 minus 1, which is in fact -10. Take these values, let's plot them, and then connect your dots. And here is your parabola. Again, notice that it is flipped upside down, so there's your parabola. Next up, 3 parentheses, x minus 4 squared. There's no transformation out here, so this has been moved right 4 and then up none. So right 4, up none. So your vertex is going to be at 4, 0 right here. Plug some values in on each side. Now this is a +3, so it should be an upward shaped parabola. So we can plug in 3, 2, and 1 on one side, 5, 6, and 7 on the other side. 5, 6, and 7 is going to be a little bit easier to plug in. So let's do that, and here's what you're going to get. Okay, now let's actually plot our points. You got 3, 3, mirror image, should be another one on this side. You got 6, 12, and I don't think any of the rest of them are going to fit, so your parabola is going to look something like that. Next problem, number 12. We're back to piecewise functions. Your -2 is going to be your separation point. Let me zoom out just a little bit so I can try to get both of these on there. So I'm going to put a -2 on my graph to show me where to divide my two graphs. Okay, to the left of -2, I'm going to graph a simple line. So -1/2 x minus 6, y equals -1/2 x minus 6, and that's what I'm graphing in the first portion over here. So let me do 1, 2, 3, 4, 5, -6. I've got a downhill line, so down 1 over 2 would be over here, up 1 over 2. Now, let's see, we're only doing less than -2, so we're going to do an open circle here. And then up 1 over 2, my graph is going to be present on this side. So there's my line. Connect your dots and erase any part that you don't need for your graph. Your next part of your graph, we're going to graph x minus 1 squared minus 5 to the right of that line. My vertex, let's see, the -1 moves it right 1, the -5 moves it down 5, so right 1 from the origin. Right 1, down 1, 2, 3, 4. My vertex is at 1, -5. And that vertex, I can do a solid circle because that is going to be part of my graph. Now to find other dots, to find other points, I can do me a little t-table. I can plug in values to the right and left. And again, it would only make sense. Why not just plug in values on one side? Because you're going to have the other side when you do the mirror image. So I'm going to plug in like 2, 3, and 4. And when you plug in 2, 3, and 4, here's what you'll get. And now let's plot those points. When I plugged in 2, I got -4. When I plugged in 3, I got -1. And when I plugged in 4, I got 1, 2, 3, 4. And again, if we use our axis of symmetry, we can mirror to the other side as well. So there's one going to be there. There's going to be a point here, and there's going to be a point here. And I am going to do a solid circle. Well, am I going to do a solid circle? Notice that this one also does not include. So let me erase that. And let's do an open circle there. So my parabola looks like that. It's going to come up to here, and it's going to go up to the other side. And again, I'm doing an arrow on this side because I continue on. However, my graph stops for my parabola here, so I'm going to do an open circle with no arrow. And they don't ask us for domain and range. The next one, again, we have a piecewise function. Our separation point is at x equals 1, so let's draw that line. Okay, now my graph, I'm graphing a parabola to the left of the line. It is -2x squared plus 6. Let's talk about transformations. The -2 is going to flip it over. Inside with the, if you need to write it like this, inside with the x, I have nothing. So these two values are going to be the same. I'm going to move it left 0 and up 6. So therefore, my vertex is going to be at 1, 2, 3, 4, 5, 0, 6. And again, I did a solid circle because that will be part of my graph. I'm going to plug in values on each side. So let's do me a little table here. Again, I would just plug in values on one side. And even though this side over here is not going to be part of my graph, I can mirror it to where it will be part. So I'm going to plug in 1, 2, and 3, which is to the right of this x value of 0. So when I plug these in, here's what I get. Now we got to be cautious as we did plug these in. Make sure you square first. Like when I plug in 2, you got to do 2 to the second power, which is 4. Then you multiply by -2, which would be -2 times 4 is -8. When you add 6, that'd give you the -2. So let's plot those points. But again, only values to the left of 1 or equal to, we are going to count the ones on the line, are going to be on my graph. So even though I plugged in 2 and 3, that's not part of my graph. So why did I do that? Let's take a look at it. When I plug in 1, I got 4. So we are going to do a solid circle because once again, it's on my graph because it's or equal to. If I have that dot, then I can also mirror it on this side. When I plug in 2, I got -2. So go over to 2, -2. However, that's not going to be part of my graph. But what I can do is I can come over to the other side and I can mirror it. And you might say, well, why didn't you just plug in -2 instead? And it's honestly just so I don't have to work with the negatives as much. So therefore, we also plugged in 3 and got -12. I don't think that's going to fit. So my parabola is going to look like this. I'm going to come to this side. Then it's going to come to here and it's going to stop because we're only going to graph that to the left of that line. So I can erase that point now. And now to the right of the line, I'm graphing -3x plus 4. My slope's -3, my y-intercept's 4. So I'm going to go 1, 2, 3, 4 is my y-intercept. Rise -3, run 1. I did an open circle because, again, it does not include 1. So open circle on the line and continue on with your slope of -3. Now it can include these points because we're to the right of the line. So my line is going to look something like that, and I can erase any point that's not on the line, and there's my piecewise graph. Next up, we're going to get some extra practice with our inequalities. So we have y is less than, so same set of steps. Look for your transformations to find your vertex, so right 3 and up 0, so my vertex is going to be at 3, 0. We're going to plug in points on either side. 4, 5, and 6 would be pretty easy to plug in because you're subtracting 3 from it. 2, 1, and 0 should be perfect mirror images. So when we plug these values in, here's what we get. And again, I can again show you, make sure when you're plugging these in to this that you subtract first. So let's plug in 6. Let's find f of 6 here. When you plug in 6, we're going to do 6 minus 3, which is 3. Leave it in parentheses, leave the negative in front of it. Okay? The reason for that is you must square first and then put the negative in front of it. So you would get -9, which we see here. So again, my vertex was at 3, 0. Let's plot the rest of these points. Now pointing out because of the less than symbol, we're going to dot our line, or dot our parabola, not line. So we got our dashes here, arrows on the ends because it extends forever. And since it's less than, we're going to shade below all the points, which would be on the inside of the parabola. And the next one, transformation, left 1 down 7. That's your vertex. Left 1 down 7. -1, -7 is your vertex. So left 1 down 7, I believe, is right there. Now let's pick some points on each side. We can go up 1, that'd be 0, 1, and 2, and down 1 be -2, -3, and -4. When we plug those in, plugging in 0, again, add first. That'd be 1. So 4 times 1 to the second minus 7. 4 times 1 would be 4, minus 7 would be a -3. And again, you can mirror that to the other side. Do that for all of your points. And there's what you get. Let's plot our points. So 0, -3. And there's what they'll look like. They won't hardly fit on our line or on our graph. We have or equal to, so we are going to do a solid parabola. And it'll look something like that. Since we are doing greater than or equal to, greater says to shade above every point, so we're going to shade to the inside. So my parabola will look something like that. So every point on the inside of this parabola is a solution to this inequality.